Welcome, everybody. This is part of the Action Team webinar series. There have been a few of these already, and today we're very, very excited to host Titomic with Jim and Neil. I want to give a couple announcements, a few ground rules before we get started. So first off, this is the Action Series leading up to the CSAT and LSAT conferences. That conference is May 20th through 22nd. The registration is still open currently, and there is a virtual option as well for those of you who are not able to attend in person. We know there's a lot of travel restrictions, both with the government side of things and in private industry. So if you cannot attend in person, there is that virtual option. We have one more webinar in this series coming up on June 12th, and we look forward to seeing some or all of you there if you are able. And last but not least, as we go through the presentation here, everyone except for the presenters themselves is muted, and we have a Q&A function down in your menu bar. If you would like to ask questions, please enter them through the Q&A function. We will be going through and reading those off at the end. I will be presenting those questions to our presenters. So without any further ado, again, introducing Jim and Neil from Titomic. Guys, take it away.
Well, thanks. Well, I guess good morning, good afternoon, and good night for you, Neil. I'm Jim Simpson. I'm the CEO of Titomic. First, I want to thank Solvis Global and the Cold Spray Action Team for organizing today's session. It's a pleasure to join so many distinguished leaders who are shaping the future of manufacturing innovation. At Titomic, our mission is clear, to make manufacturing innovation a reality through our kinetic fusion, a technology that fundamentally transforms how we design, build, and sustain critical systems for defense, aerospace, energy, and infrastructure. I want to introduce Neil Matthews. Neil is our Senior Technology Fellow, and Neil, why don't you say a few words, please?
Oh, thank you, Jim. Yes, it's a pleasure to be here. I've been involved in a previous webinar. It's exciting because, as Jim will explain, we really have started to grow significantly, and in many cases achieve significant development, both on manufacture and also in repair and coating. So I'll hang in here with Jim, and certainly if there are any questions at the end that I can help, I'll certainly do that. And if there's any comment that Jim would like me to make, I can certainly contribute as we go along. So thank you very much, Jim.
Well, I'm not a psychic, but I'm pretty sure I'll be calling on you quite a bit. So I think we've already seen us. So, who is Titomic and what is Titomic and kinetic fusion? Titomic is a world leader in the kinetic fusion. It's a proprietary additive manufacturing process based on cold spray principles, but with a level of sophistication, scale, and material performance that positions it as a strategic enabler for modern manufacturing. Unlike traditional fabrication methods that rely on the welding and melting, kinetic fusion uses supersonic particle disposition at a near ambient temperature. We join the metals together through solid state kinetic energy rather than heat. And Neil, what do you call it? Ambient? What's the term that you like to use?
I usually like to call it adiabatic shear. So it's a phenomenon where under that transfer of kinetic energy, you get the bonding at the boundary layer through an instantaneous fusion. So I think it's got many names, and in some cases very, very difficult to explain. But I think the important thing is it's that transfer of energy with that fusion at the boundary layer of each particle.
Yeah, and the results are structurally sound, oxidation-free, distortion-free builds. I mean, we're achieving in titanium with our high pressure system up to 97% of the theoretical density of titanium. So it shows that through kinetic energy, we are actually able to plastically deform and cold fuse the materials to almost the theoretical properties of the base material. It allows us also to work with advanced materials like titanium, nickel alloys, and refractory metals, even combining them into some novel gradient structures. The bottom line is that simple, is that kinetic fusion enables parts to be built faster, stronger, larger, and more reliably, unlocking geometries and material combinations that simply are not feasible with traditional techniques. And I think one of the other key elements, and we'll talk about it even more, is that because we don't heat it up, we don't have thermal distortions either. part of some of the road that we've been on, we are ISO 9001, we are AS 9100, and ISO 27001 certified. We'll talk a little bit more about the qualification processes we're going through now. But the key elements are that one of the things is that we're really moving from is more from a research and development to actually a certified process for aerospace, defense, oil, gas, and energy. One of the things, so I joined about 6 months ago as the CEO. We are based, as Neil is right now, in Melbourne, Australia. That is our current headquarters. We focus there in the Melbourne activity as we have the capabilities for low pressure, our 523 for coatings, medium pressure system, which we'll talk about, that we're actually also doing coatings, but we can do coatings with materials as robust as titanium. And then we go to our high pressure machines, which can go up to 12 kilometers per second from a velocity perspective. And hence we can do refractory and titanium type of materials at close to their theoretical densities. In the Melbourne facility, we do a substantial amount of our research and development, as well as a lot of our production activities. We also do coatings there, but that's our focus is in the production area. In Akram, in the Netherlands, our focus is more in machine building. We do a lot of coating activities. We have a program there with Airbus and others to do some support their aircraft activities for MRO, for coatings for non-critical flight hardware. Again, Akram is also a full capable facility that has the ability to do high pressure capabilities as well as the low pressure coatings. But our primary focus there is in the coating area and also the machine build. Very recently, we created a headquarters in California, in Huntsville, Alabama. I'm in California, by the way, right now. But in Huntsville, Alabama, a 59,000 square foot facility, formerly was the Pratt Whitney engine manufacturing facility. It happens to be very well suited for our capabilities as far as kinetic fusion additive manufacturing. We're very excited about that pivot into the United States. This will be not only our global headquarters eventually, but also it is where we do all of our manufacturing for the United States. And this will be a full capability system. We actually have our ribbon cutting on June 2nd. If people are interested in visiting the facility, we'll be happy to give you an invite. That's where we will be located. We're doing a lot of activities right now for the defense and aerospace area there, as well as maritime and oil and gas. So a fully global capability that we've got, and frankly, with the current world order, this seems to be really well suited for what's going on in the dynamics in the world. From an economic efficiency area, kinetic fusion is more than just a novel process. It's a national capability. It directly addresses supply chain vulnerabilities by allowing rapid local production of critical components. It extends the operational life of aging systems through superior sustainment and refurbishment. It enables faster fielding of next generation designs of removing tooling bottlenecks and material limitations. And it provides new pathways for in-space manufacturing, radiation shielding, and hypersonic system development. Whether it's repairing a corroded naval asset, or building pressure vessels for satellites, or creating thermal stable nozzles for propulsion systems, kinetic fusion is ready to deliver. And so, one of the things that we're talking about here, and Neil can interject on this, is that one of the key elements that we do have is that because we are additive manufacturing, and actually our additive manufacturing really is not, we don't build the most complex parts in the world. We build parts rapidly. We build parts with great performance, close to the theoretical properties of the base materials. and we build large parts, and we build them quickly, but we do not build the most complex parts in the world, which typically you get used to with, I'll say, uh, laser beam additive manufacturing and others. But what we do well is we build parts very quickly without thermal distortion and with very good properties. Just like other, and if you want to compare us, I think, Neil, and correct me, but part of it is that if you want to look at us, we're kind of an alternative to WAM, we're an alternative to investment casting, and we're an alternative to forging, where we have much less material utilization. In fact, we only have about 10 to 15% waste versus up to 50 to 70% for investment casting. And we're able to mix different materials without having thermal distortion like the other ones. And so, Neil, if you would like to interject a bit as well.
Yeah, so I think one of the major things is when we talk about large scale, we really are talking about large scale. So probably even in some of the areas where the normal traditional casting and forging and those sorts of things, we're able to produce very, very large items and things like that. And the irony of it is that it's that quite often it's not the ability to build large items, it's the ability to actually post-process them, which is the limitation. So what we're effectively saying is that this technology is really unlimited in terms of build. Yes, you've got to do some smart things to manage residual stresses and those sorts of things, but even on the image you see there, that's quite a significant part, and it doesn't take us that long to build these parts. And confirm what Jim's saying. The real benefit of this is very, very large, what we call thin-walled or thin components, or very, very complex parts in as much as layered builds, not in terms of the shape of it, but just the ability to multi-layer build. So all of those sorts of things are now with us. We're demonstrating that, so we know what we're doing, and certainly we're putting down large amounts of powder over a lot of time that would be unmatched by any other technology.
Yeah,
Thanks,
to
Jim.
put things in perspective, we recently, and we believe it's the largest part ever built by Kinetic Fusion Cold Spray, a 175 kilogram part. We built that in less than 72 hours. So this is an example of how quickly we can build these types of parts at full density. So again, a very exciting aspect of things that we're doing at this point. So some of the things that we've been talking about here, and some of the things that we've actually been alluding to, um, when we talk about what Neil was talking about as far as some of the complexities that we can do relative to our materials, is that because we don't melt the materials, we can create some rather unique, I'll say, continuums of materials, going from a base material to actually doing a continuum or a gradient in which we can be moving the coefficient of thermal expansion such that we can go from a very malleable material to something that could even be a metal matrix composite or a metal matrix ceramic type of a capability, which allows us to do some very unique things relative to radiation hardening, uh, uh, ballistic armament, and also for other types of applications. And so we're really quite excited about that kind of capability. Because we're able to do these types of mixes, we're actually to create very lightweight, very wear-resistant types of parts, and we're able to do this at speeds that others cannot do. And again, our ability to be able to mix different powders, our ability to be able to utilize different powders is quite unique as well. We're able to do, with our capability, utilize anything from spherical powders to titanium sponge. And Neil, maybe you'd like to comment a bit too.
Yeah, again, what we see here is particularly the low cost of titanium sponge and the ability to, through the cold spray process, and it's quite challenging because many of the parameters, the actual build parameters, we have to optimize. And we are now in a situation where we build very, very high quality titanium, not far from TI6, but it's from base material. And the beauty about that is becomes very, very cost effective, and is almost in some instances comparable to steel. For the hybrid parts, again, we've had the opportunity on one occasion to put something in space, and it was basically a thermal dispensation build, and that's working very, very effectively. So we have a lot of confidence that we can build this layered material for hypersonics, for space programs. And as far as armament goes, we've already demonstrated that we can successfully build lightweight armor plate, again with the use of titanium, which would meet the customer's requirement.
Great. So we've been talking actually a little bit about this, is that some of the things that we're capable of looking at, and some of the different types of capabilities that we're able to have. Kinetic Fusion's already delivering impact across multiple sectors, from a defense perspective, creating lightweight corrosion-resistant structures for aircraft, ground vehicles, and missiles, and sustainment of legacy fleets and rapid prototyping of advanced concepts. In the aerospace and defense systems, radiation-hardened satellite components, micrometeorite-resistant coatings, and pressure vessels built faster and stronger for orbital and deep space missions. And then in the maritime and infrastructural area, corrosion mitigation for naval fleets, barges, and port infrastructure, dramatically reducing some of the life cycle and downtime. And then in the energy and heavy industry area, we repair and reinforcement of critical systems operating in extreme environments such as oil rigs, pipelines, and power generation. The reason I bring that up on this powder technology activity is that we're able to to tailor the powders and actually the types of pressures that we're going to be applying the materials based on the different machines we have, and also with the different types of powders that we're able to utilize. We recently have agreements with 5 of the domestic providers of titanium powders in the United States, all with varying types of powders that we're certifying through for Titomic. And this provides some of the different types of capabilities that we're looking at here. And Neil, maybe you could talk a little bit about some of the things that we are doing as far as tailoring the powders to be able to accommodate, anything from electromagnetic interference to directed energy weapon protection.
Yes, I think the element here is the ability to build and define exactly the powder type and the morphology in particular. We find that certain morphologies perform better in the applications we've got. Particularly with titanium, we probably are well versed, and probably one of the most well versed companies in terms of the oxygen and oxygen at boundary layers and all sorts of things, and the impact it does have on the performance. So again, it's what we're doing there is we're actually tailoring our parameters along with powder morphology to basically achieve some of the requirements. And some of those requirements can be, as we've already seen, impact resistance, fracture toughness, fracture behavior, all sorts of elements which the customer may or may not require. But we can tailor a base powder to meet all of those sorts of parameters of strength and ductility and those sorts of things. It's always going to be what people would call a compromise. I call it a balance of mechanical performance, but they can all be adjusted through the parameters you use during spraying. Thanks, Jim.
Thanks. We talked about the domestic powder suppliers. One of the things, obviously, that we've been very concerned about with as the United States goes to a more protectionism type of an environment, and we're doing a lot more onshoring. How do we make sure that we assure that we have these kind of capabilities in the United States as well as in the Netherlands and in Australia? And having this domestic powder supply collaboration has been a very essential key for us.
And sorry, Jim, there, I think what we clearly clearly identify not all powders are the same, even though they may look the same and even may have a reasonable pedigree. No, I would say no two powders are the same. So again, there's a lot of work and a lot of understanding that's required to utilise these powders to their optimum. And that's why it's so important to identify a range of powder suppliers, because there may well be within that basket of powders, different powders from different suppliers that we can use to achieve different outcomes.
Yeah, and we're talking about U.S. here, but we've been engaging with the Australian government and European governments as well as the U.S. government to certify and qualify our kinetic fusion for defense and aerospace qualifications. In fact, we recently started the certification process with DNV for maritime and oil and gas activities, as well as working now with U.S. With NASA and others to try to provide certification for our processes. So this is an ongoing activity. It is a collaboration. We're partnering obviously with primes and also with our suppliers to enable us to have this type of certification so that we can be working on programs of record and not doing R&D.
And again there, Jim, I think that's probably one of the greatest challenges, not only for the coal spray community, but for AM in general, is the necessity to engage with customers, to align the specs, and in some cases, as we have done, co-author specifications for the coal spray additive manufacturing. There's not a lot out there. So the normal requirements of normal metals don't really apply. So yes, we have to spend a lot of time to make sure we understand the customer's requirements for certification and acceptance, and go down that pathway to ensure that we provide all the evidence that we need. And we're doing that proactively and in parallel with some of our product development.
Well, in fact, Neil, you've been working and we were successful as far as getting the SAE 7057 process approved here very recently.
Yes, that's correct. Yep.
So where are we as far as technology readiness levels? Because we've been talking about how we get certified in production. Is that we have we're in a variation in the different types of TRLs in multiple applications for commercial and government pilots. We're at a TRL level 6 or 7. In other cases, we're at TRL levels 3 to 4. But we do have one activity that we've been doing with the Australian company Spirit called the Hermes satellite, in which we developed a thermal radiator that's been flying in space now for over 2 years, which is at a TRL level 9. So there's a lot of variation as far as the different TRL levels, but we're trying to mature the process as quickly as possible. And Neil, maybe you'd like to talk a little bit about that.
Yes, again, it's one of the elements of engaging the customer. We certainly do that a number of ways. Where we are very, very close, we obviously engage the customer for trials, and we certainly see that on the space programs. We've got items in service that have been repaired and those sorts of things. So that's basically to just go to that last step. But we also have collaborative programs with universities, with research agencies and things like that, to basically accelerate those ones that are at 4, 5 and 6, to accelerate them so that we can go straight into the commercialization. So those agreements are such that when we engage in these collaborative agreements, we always focus on ensuring that the whole program of development is focused on the commercial outcomes and their industry requirements. So there's a thing called the Valley of Death, and we hope we've built bridges in many cases to accelerate that. And I think that's one of the programs that we're working on now in Australia, which has just been announced, which is a large AM, additive manufacturing collaborative research program. I think it's about nearly $200 million, which is a lot of money for Australia. But certainly the important thing is there to work with end customers and the academic and research, so that we can work collectively in parallel to reduce the TRL maturity timelines. Thanks, Jim.
And we're taking that model that that Neil just talked about and moving that to the United States when we in our global headquarters at Huntsville, Alabama. We are building partnerships with the primes, the national laboratories, NASA, and the DoD. We're advancing the material qualification efforts through collaboration with universities such as the University of Alabama, Huntsville, and also with NASA Marshall. And we're developing certified manufacturing capabilities to support critical programs across aerospace, maritime, and infrastructure sectors. So this is an ongoing activity, one of the areas that we're really focused in on at Titomic. So, part of the certification acceleration, how do we go faster and how do we make sure that we're doing the processes correctly? And so, as we've been talking about a lot here, is that we have been doing a lot of collaboration with the prime contractors and with government agencies and international agencies to get the certification process going as quickly as possible. One of the other aspects that we're doing and we're working on right now is how do we assure that our processes are mimicked appropriately across the industry. And if someone is utilizing our machines, how are we making sure that that we're actually getting the right products out? Because clearly we don't want someone to, I use the example is that if you give somebody a set of golf clubs, they don't become a pro golfer overnight. Just like if we gave a person one of our machines, they're not going to be able to do cold spraying overnight. There is a lot of technique to it relative as well as science. And so we're actually trying to accelerate some of those activities by creating what we call a mixed reality a goggle. The goggle will actually allow a technician to be able to point out different areas of damage. They will be able to then show that in the goggles to another technician or that same technician. There will be a drop-down menu as far as the different the processes so that we can assure that the processes are done accurately. There is actually a sensor that will assure that the tip of the nozzle of the sprayer will be at the appropriate distance so that we can assure as best as possible that capability will be done properly. We actually then collect that data in 3D in a digital twin for archival approaches. And then the other aspect that we're looking at here is that we're also controlling a lot of the powders as well as the training. So, one of the things that we're trying to do, maybe not quite as dramatic as what Hewlett Packard did with their inkjet printers, but we nevertheless are assuring that the powders that we're utilizing for our system are certified by us to make sure that we've got the right sourcing. And these are things that are absolutely critical as far as the cold spray additive manufacturing, because it still really is a rather new advanced process. Neil, maybe you'd like to comment a bit.
Yeah, I think the good thing about having a global presence is obviously you can access similar markets and similar industries around the world. The key there is, though, that we've got to make sure that we've got repeatability, reliability, and it's transferable. So we are paying a lot of attention to make sure that we get the quality procedures right, the processes right, and all of those things. We talk about the powder supplier, and all of that's there mainly to be able to basically transition between sites as we grow and as the need arises, because I think most of us that understand quality at the moment would understand that AM is parameter driven, input parameter driven. What we're trying to do is to make sure that as we develop machineries, we use technologies to monitor output and use that hopefully in the future to be able to assure quality, because that'll be a continuous record gathering. But as I say, from a global perspective, it's so important that we all do the same thing and are able to transfer things easily. And that's all part of the certification process. Thanks, Jim.
Thanks. I talked a bit about this already, but the key different industry applications, but because of our ability to be able to utilize refractory metals, be able to use titanium, frankly, it's a natural for aerospace and defense applications. Aside from aluminum, titanium is the most used metal in aerospace and defense. And frankly, our ability to be able to use it efficiently, which allows us to have sustainment, and also to be able to do it rather quickly without thermal distortion with great performance, that this is really been exciting for the aerospace and the defense community. And then if we talk about Navy and maritime, I think that, one of the things that we always talk about is that, we like corrosion because frankly, our capabilities with our low and medium pressure capabilities are able to resolve a lot of the corrosion issues in Navy and maritime and oil and gas applications. The other thing that's quite exciting is that in the oil and gas area, because we don't heat up the material, we don't have to evacuate the oil rig while we're doing a repair, which obviously is something that you could not do with welding or other options. So this is becoming quite exciting for the companies that we're working with right now, which are Woodside and Equinor and Able and others, to not just do corrosion resistance, but also to do repair in situ of valves and other applications. So we're starting to see that because of the capabilities we have, because we don't heat up the material, we're seeing that the benefits are really tailored for these markets that we're focusing in on. Neil, maybe you'd like to talk a little bit about this as well.
Yeah, I think from the oil and gas perspective, it's been again another collaboration where in fact they've defined the test requirements, they've defined the corrosion envelopes, they've been actually managing a lot of the verification and validation of corrosion resistance through research agencies and things like that. So again, we have here a partner, if you like, an industry partner that's really looking for solutions. He has no real solutions at the moment for the corrosion. He's got temporary repairs and things like that, but he doesn't have any real-time permanent solution. So he's been helping us along the way. He's been helping us to select the coating. He's been helping us to drive our solution, and that's why we talk about the 623. He's quite happy with the low pressure solution, but he wasn't overly excited about the area of coverage. So one of the elements of the 623 is to hear and listen to what he was talking about, and to provide him now with a system that gives him a huge factor increase in area coverage. So I think, again, it highlights the fact that customers will work with us to develop a solution for their needs.
Yeah, and Neil, I'll kind of foot stomp that, is that the 523 was a great machine, and when Woodside was doing it, they were very excited about the corrosion resistance. In fact, they were seeing that they believed that some of the corrosion repairs that they had could last up to 15 years. The problem was that you're using a system that's almost like a pen, and try to visualize even drawing in a 2 foot by 2 foot activity with a pen. It's just a laborious process. So the 623, which does these types of capabilities as well, is able to push powders at 30 times the amount that a 523 is. And so while this is excellent for very unique scratches and other things, the 623 is able to do much larger areas very quickly. And so it's become quite an exciting breakthrough as far as our coating and corrosion resistant activities. We talked a bit about the MRO operations as well as some of the things in the energy sector, but in the MRO area, we're seeing that the ability to be able to repair the materials back to their base material for aviation has become something quite exciting. What we're seeing is that the evolution from non-flight critical hardware to actually starting to look at some flight critical hardware for our operations. Right now, we're in the midst of, actually, there is one company that's already using our system for their MRO applications, and then we're in the midst of the process to certify the process for Airbus for use for their MROs. So there's quite a we're quite excited about this area. We're working with all of the major aircraft manufacturers to for their MRO applications and doing the training and making sure that we control the properties such as the powders and the training as well. So this collaboration with the different aircraft manufacturers has become an area that we see is growing quite a bit in the near future. Neil, maybe you'd like to comment a bit.
Yeah, I think that's very true. Obviously, what we would hope to see, and we think it will happen probably over the next few years, is the move from non-structural or non-load credit repairs into the other repairs. We see that happening. We fully understand that we will need to provide damage tolerant and durability coatings and all those sorts of things. There's been many papers written how it is effective and along those lines. The other element I'd like to just mention on the MRO sector is we have had the 523 in operation in the Ukraine through our Netherlands activity. The reports we're getting back, they are using that very, very effectively. Obviously, we don't know what they're using and things like that, but I think again, it highlights the opportunity of the technology that you can take it into theatre and you can use it on the target. So that's very, very encouraging as we go forward. So thank you, Jim.
Yeah, and you know, again, we've the feedback we got from the Royal Dutch Army was that Ukraine was using this in the field. So we're actually doing real-time repairs, and that was very unique relative to some other of the cold spray applications that they were looking at. So we're quite excited about, I'll say, the mobility of our system and the ability to be able to use in situ and in field. We've talked a bit about the diversity of our cold spray systems. We're able to like we talked about in the field, in situ, we're able to use our mobile machines, the lower and the medium pressure systems for the D623 and the D523. These again are for the more malleable metals such as copper, aluminum, nickel, stainless steel, Inconel, and others. We actually can go up on the 623 because of the pressures up to titanium. We do have controlled spray booths with robotic capabilities to be able to have more precision. We then move to the higher pressure machines, the TKF 1000, and then we have a TKF 325. This is pretty scientific, the 1000 and the 325. That means that the TKF 1000 happens to be able to do parts of about a meter. 3.25, it means that they can do 3.25 meters. So we spent hours and hours on naming these machines, being sarcastic, of course. We have actually built a custom machine up to a 9-meter capability. So we do have a lot of flexibility, and what we talked about is the large parts, and Neil brought that up as well. So again, if we looked at it, the 623 and the 523 really focus primarily on coatings, layers like that, where when we go to the TKF 1000, the 325, etc., that we're focusing more on the production. On the right-hand side, those are the higher pressure machines. They are the ones that we utilize for the refractory metals, for titanium, and then on the more malleable on the 623 and the 523. And Neil, maybe you'd like to comment a little bit.
Yeah, I think if you look at the image of the 523 and the 623, what that really is saying is, yes, if you buy a standard one or get a standard one, it comes in a blue box. But what we're doing is it's very, very adaptable, and all our machines are very, very adaptable. And we are making, let's say, versions of it for Army installation on vehicles, and that requires repackaging. So I think the significant thing about the 523 and the 623, they can be packaged for mobile applications. If you look at the integrated spray booth, that's there mainly for the academic institutions, so they can get access to the technology. It's all kitted out. We have a number of those being sold in Europe, and it gives the educator an opportunity to introduce cold spray into that early part of training and education, both at the trade level and at the engineering level. And it also gives them the ability to play with materials. And as Jim says, the TKF, the big ones, are purposely built for customer needs or for customer products, so they can be tailored. So thanks, Jim.
Thanks. So we've been talking about, some of the key elements that all along that we're really focused in on in the powder innovation, obviously looking at different types of powders, all the way from, titanium sponge to spherical powders. We're looking at different blends of powders to be able to create very unique materials for tailored applications. We're working very hard to make sure that the processes are very repeatable. If there's one thing that we're really working on dramatically, is to make sure that the parts that we're building are repeatable, because that's absolutely essential for the different markets that we're focusing in on. We have been looking at, how do we, we're looking at, from a technician perspective, how do we make it easier for them? Which is definitely designed for different types of sprays, as far as the amount of powder that we can put on a surface at a time. We've talking about how do we make sure that we can share our data, so and also that we can be assured that we're following processes. So we are very focused on getting certified and following standards. And then right now, and Neil's talked about it a little bit with the what we're doing with the universities, but we're working to develop courses for the technicians to be able to utilize our capabilities, as well as developing the R&D that's required for some of the powder activities, as well as how do we apply it with different pressures, different velocities. How do we reduce thermal stresses in the systems as well? So all in all, the key is that, how do we make this more consistent? How do we make it more useful, and how we can tailor it for the different applications? And Neil, maybe you'd like to comment a little bit.
Yeah, I think I look at the title, Unlocking the Full Potential, What's Next? And this is going to carbon date me, but when I got involved in the technology in 2004, and it was looking at corrosion protection, that's what it was for. It wasn't even about restoration and things like that. And I see where we are now. So I can't imagine what's coming next. I think what we're talking about here is the ability to engage other technologies. I think the ability to utilize AI, which we'll talk about a bit later, maybe look at the potential to integrate some of the other thermal activities, like maybe we can use laser for post-heat treating and all sorts of things. So I think what we're saying here is that there are things within our control, and that's what we're looking at them. But those key elements that are identified there, certification and standards, we could be, making wonderful, wonderful things, but if it doesn't get and pass those criteria, it was a good idea. That's all it was. So I think the whole thing here is that there are so many opportunities we're now seeing, and the ones we don't see, people ask us, can you do it? And I think that's one of the more exciting things, is that we're not the keeper of all knowledge and all potential. Customers are asking us what we can and can't do. Now, that's not to say that, there are things we can't do, but it's interesting that a lot of our engagement now is on people asking, can we do this? So I think it's a very difficult question to answer, what's next, because we can only go where the technology will take us, and it's already taken us a long way.
Yeah, and you think of all the different infinite amount of different types of mixtures we can create, and we're actually now focusing in on some other things like scalmalloy and other super alloys for powder metal, or for the powder activities as well. So it has been extremely exciting, and as Neil pointed out, and we talked about a bit with the mixed reality, is that we're starting to focus more and more on our artificial intelligence applications as well. In fact, we did talk about this already. I'm not sure, Neil, if you'd like to add a little bit more, but we have been really focusing on making sure that we're more consistent, that more people can use this appropriately. But Neil, maybe you'd like to add a little bit.
Yeah, I think one of the elements here is that we often get ask can we or what if and those sorts of things, what we're now finding is that we're getting very, very close to be able to model. Because if you look at the fundamental element of accelerating particles and transitioning to kinetic energy and things like that, so we are becoming closer and closer aligned to some of the digital twins and the virtual and the visualization. I think that's one of the most exciting things is a lot of work's been done, and it's been done all around the world. We're doing it in 2 places, and I know a lot of it's been done in the US as well. But we are very, very close to having very, very high predictable models. And even those models now are extending into the ability to predict density, some of the mechanical properties and those sorts of things. So once you look at the ability to visualize without going through a huge amount of sample and things, samples will be there to validate the models, not the way we've seen it in the past, where we create models on the basis of what we achieve. So we're very, very close, and to be able to integrate that in the whole process, the tool path, the virtual twins, and all of those sorts is very exciting. Thanks, Jim.
Yeah, no, that's great. And so we talked about, I think in closing, Titomic believes that the kinetic fusion, it represents transformational opportunity, a way to build faster with better materials, greater resilience, and lower life cycle costs. A way to ensure security, self-sufficiency, and competitiveness on the U.S. industrial base, and a way to unlock some of the innovation across defense, aerospace, maritime, and beyond. We're proud to lead this charge, and we're eager to partner with many of you to deliver the full potential of kinetic fusion. And I think on behalf of Neil and myself, thank you very much, and I think we're open for questions.
Okay, thanks so much, guys. That was a wonderfully delivered presentation. We do have a handful of these, so I think I'll probably just cherry pick 3 or 4 of them and toss them your way. So the first one surrounds qualification and the approach for qualification in high performance and regulated applications. So what has been your strategy and the approach to actually get something qualified for an application like critical hardware? How are you working with the customer with a process that's, like you said, doesn't have a lot of public standardization or experience around it to actually do that?
I'm going to start, and then Neil will correct me appropriately. But I'll say at a very top level, we are getting our materials qualified. In fact, in some of the primes activities, we're actually working towards being an enterprise process, but that takes time. A lot of material property data. How do we make the processes uniform and consistent and predictable? And the problem that we deal with when we're dealing with the primes is that each prime they will certify it, but for them, and we can't share that data typically across the board. So in parallel to that, we're also working with government agencies such as NASA, such as the Department of Defense, to be able to qualify our system so that we can be able to share that data broadly across the entire community. And so we're doing, I'll say, in both cases. And then, as I talked about earlier, in the oil and gas area, we actually are certifying again at the prime level, but also we've got the DNV involved now to be able to qualify us for coatings as well as for products. So the focus has been to do the qualification with the primes to get a lot of learning. But again, the whole key is so that we can share this across the community, and so we're getting our certifications involved with the government's agencies as well. And working with NASA actually it works out quite well, because there's a relationship with ESA, which allows ESA to recognize NASA certifications. So we're trying to spread it that way as well. And then because of AUKUS, we're able to share things as well. So you're seeing more and more. That's our approach at qualification. But obviously, there's the details associated with the qualification that I'll let Neil talk about.
Well, you did a good summary there, Jim. I think the whole thing is there's normally a number of players in finally getting your product on, I guess, on whatever you want to do. So invariably, industries do have an overarching regulator. And that regulator is obviously looking at things like safety and a whole range of things. So his requirements could be very, very specific or very, very broad. Underneath that would be the design authority or the engineering authority or whatever, that basically, again, makes sure that the product meets the requirement. And embedded in that is the quality organisation that is looking at repeatability and reliability. So you really have to think about all of these players, because they will all tick things off. One of the areas, and we get back to why did we sponsor a cold spray additive manufacturing SAE or an AMS? The reason was none existed. And it's very, very hard if you don't have existing sort of general AMSs and ASTMs and things like that. So, and there'll have to be an AMS for repair and probably one for coating and those sorts of things, so that embedded in the from the regulator, he will look to what other elements you're looking at. So it's not easy, but again, if you start off with the overseeing of the regulator and make sure that at least you get him on board, and then bury down into the respective design authorities, I'd call them, or the engineering authorities, to make sure that they'll buy off on it as well.
And I will say there's a couple of unique approaches. That one, obviously, the I'll say a full certification approach where there's controls on the powders, etc. And then there's the other approach that people are utilizing, I'll say for maybe more onesie twosie type of activities, where they qualify the part versus they qualify the process. And so it's a rather unique spectrum, but we're really focusing in on the end that gets us qualification for our whole process and how we utilize our powders, etc.
Awesome. Thank you so much. I think two more and then we'll call it time. So first, you guys have mentioned that there are low, medium, and high pressure systems. What are you calling medium pressure? And for you, is medium pressure including the traditional injection behind the throat of the nozzle that you see in high pressure, or is it downstream like you see in low pressure? What's the offering really look like there?
I'll defer to Neil for that one.
Look, the nomenclature of high, medium, and low are very, very subjective. Let's look at that. So what we're looking at is what we call a low pressure system is akin to what everybody else uses. And if I was to say it runs at 5 bar, yes, it does. Why does it run at 5 bar? Because that's shop air. What can it run at? 10 bar. If I talk about our medium pressure, what are we running at? And then I'm going to say, do you want to run air? Do you want to run nitrogen? And what materials do you want to run? So we have these grades of equipment, but the equipment really is related to the materials they spray and what's acceptable to that. If you look at most low pressure systems, they're normally a blend. They're not pure alloys. They normally have an aluminium oxide in them or a chrome or things like that, but that's fit for purpose. So yes, if you want to know, I think our low pressure is about 9. Our medium pressure at the moment is 20, but it's going to go to 35. And our high pressure, in fact, the way we operate at the moment, that's not a manufactured system. That's a tailored system. So we will use high pressure systems like plasmageekon and impact elements within that to achieve that. So it's all really, at the end of the day, and it may sound rather mundane, but it's all about particle velocities and the powder you're spraying and what's best to spray it for the application the customer needs. Yes, we've categorized them, but that's purely for torque, but it's really about the performance of each machine. And I probably haven't answered your question, but that's the best you're going to get from me.
No, I think you did. That's a great answer for this community too. We certainly appreciate the intricacies of material. So last one here, and then I think we'll cut everybody loose. Within your customer base and within your own shop, what types of process diagnostic tools are being used, and what percent of operations do you think are using them versus what percent really should use those various process diagnostic tools?
Okay, Jim, do you want me to run with that one?
Yeah, absolutely.
Okay, so the sort of diagnostic tools we're using are basically predominantly velocity cameras and things like that. We do a little bit of thermal imaging at the time. We are getting all our information to develop machine learning for some of our predictability models. So we are incorporating machine learning by recording a number of elements. So they're all the input parameters. Yes, we are looking at the output parameters, and we want to do more. But the fact of the matter is that most quality systems for cold spray deposition require you to control input parameters, and at the moment are not tuned into output parameters. We would like to have output parameters, and we do have things about the quantity of powder we're measuring and feed rates and things like that. So we have those sort of input parameters that we're monitoring. But what we're seeing is, in addition to the velocity cameras that we've got, we'd like to consider thermal imaging. But why would I want thermal imaging for cold spray? Well, we get back to another anomaly. The gas temperature is certainly not cold. And there are thermal stresses if you're not careful, particularly in large bills. So you've got to manage that. Residual stresses are very, very significant. Maybe embedding sensors during the build process. So what we're hoping that, and I'm going to go right on a limb, hopefully the quality world will realise that for this sort of technology and AM in general, it's much, much better to focus on the outputs than the inputs. Here endeth the lesson.
I'm going to add one other aspect that and I'm not going to say it's a diagnostic, but it's something that we regulate, is that we are working, to make sure that we understand the particle distribution size before we submit, the amount of oxygen content that's in the systems, et cetera. So part of I'll say the input is what is the part of the system, the powders that we're actually spraying as part of the diagnostic aspects.
Very true, Jim. Very, very true. It's so important. The powder is key.
Yeah.
All right. Well, with that, we are at 11. Thank you both. That was a wonderful webinar, and we look forward to seeing everyone at the CSAT LSAT conferences, and again for follow-on webinar if you are attending the next one. Thank you very much for your time, and again, thank you to Jim and Neil